Hey folks, welcome to DAT324. Some of you might work on a perfectly static system, one that never changes. You never have deployments, you never have customer increases in load, you never have to deal with natural disasters. But out of interest, hands up please, who works on a system like that? Somebody laughed down the front, thank you very much, that was my cue. It's because I don't think it exists, right? Change happens all the time, and the only way that we can deal with this is to be ready for it, right? Is to build our systems to be resilient. Right? So what we're going to talk about today is how you can use some high availability and disaster recovery patterns to make your Aurora system more resilient. So hi, I'm Tim Stokes, and now I'm really loud. I hope that's not too bad. And I'll be joined later by Grant McAllister. We're both senior principal engineers at AWS working on Aurora. So let's kick off. So what we're going to do is we're first going to define the term resilience a little bit precisely so that we know we're talking about the same thing together. So resilience is the ability of a workload to recover from infrastructure and service disruptions, dynamically acquire resources to scale up and down with your load, and to mitigate disruptions like transient network issues. So this is supported by two pillars, availability and disaster recovery. So there's no one solution to any of this. If you've come here for one solution, sorry, I don't have one for you. What I have is a whole landscape of these solutions. And I'm going to help you, and Grant's going to help you find the place along this landscape for which you can choose for your application where you are today and to know where the path is going to take you tomorrow with Aurora, right? So first we're going to drill into these pillars a little bit more. First one up is availability. So availability is the proportion of time that a workload is available for use. This is usually as a historical measure over a period of time, like a number of nines. Like here we have 4 nines. 99.99% of the time that we're measuring here, in this case a year, your system was available for use. So adding redundancy to a system is a powerful way of removing the single points of failure and therefore increasing your availability. Next up is disaster recovery. So these are techniques and strategies that you can use to deal with a disaster event, a single disaster event. So they focus on these one-time objectives, like RPO is the second one we'll talk about, RTO first, recovery time objective. So that's the maximum length of one impacting event, right? You might think about it as downtime when something like this happens. The second one's recovery point objective, or RPO. So this is the maximum amount of data loss that we're willing to tolerate, but it's normally measured as an amount of time. So we might say the last 1 minute or something of data we'll tolerate losing after an outage. Normally this is due to us using some kind of asynchronous technology, and we have a replication lag to deal with here. So now that we've got a common language, if you can put up with my accent, we can dive in. So I mentioned before that we have this landscape of trade-offs that we have to make. So what I'm going to do is I'm going to give you an example, and we'll work this example the whole way through. And hopefully then you can kind of see your reflection in that example a little bit and use that to color your thinking. So imagine that you're a database administrator. Probably this is easy for most of you folks in here. And you've just been hired as an administrator for a hot new startup. And they sell these cool pictures of the night sky that you can see up there. There's a joke in there, please somebody laugh. It's fantastic. All right, thank you. Cool. So in your startup, you've just got a small amount of angel investment right now. So you're starting off small. So you choose Aurora because you know it's flexible enough to start off small with you, but it's able to grow into that unicorn that we're hoping to be by the end of this talk, okay? So today we'll follow the journey of this startup, and hopefully you can find your reflection in it. So first up, the minimal configuration of Aurora. This is what you get out of the box, nothing special. It gives your database durability across 3 availability zones and availability in one of them, right? We call this the single AZ design pattern. So there's one database instance we see here in availability zone 1, and which balances your cost and performance and availability. This instance is where your query processing's done, your buffer pool lives. It's probably very familiar to you if you're coming from an on-prem situation. You can scale performance by increasing the database instance size, increasing it even further and further, vertically scaling, or maybe even using serverless where this happens for you automatically. But there's no data stored in here, right? Not like a traditional instance. So this is where Aurora is quite different. We separate the storage out, we disaggregate it into this fleet we call Aurora storage, into this abstraction we call an Aurora volume. So it might not look very interesting in this configuration, because remember, this is the first step from for your startup, right? It's the most minimal thing we can do. But it's the underpinning of what we're going to talk about later today. So we have to drill into this quite a little bit. So that volume, it's elastic in performance. It will just give you as much performance as you need. You don't have to worry about provisioned IOPS. And it's also elastic in size. It will scale up and down up to 128 terabytes according to the need of your database, right? If that one database instance becomes unavailable in that one AZ, then your system's unavailable because that was the only instance that you had. But your data is still durable. It's still stored in that Aurora storage fleet. So as soon as your database instance comes back or you provision a new one, you're back to the races, okay? So let's dive a little bit deeper in how that storage works so that we can understand some of these other features. So like I said, this is disaggregated storage across all the 3 availability zones here. And it's made up of a large number of special purpose things we call storage nodes. Here I'm just going to show you 6 of them, the big blue boxes there. Obviously there's many more than 6 in a real system. These are multi-tenant. We can see the small boxes there is my idea of trying to represent other tenants' data inside those storage nodes already, other volumes data. Now, that's already there. Now, your volume, when we write in from the top, the Aurora volume is going to be first encrypted. Your data is encrypted with the encryption key from you. And then we're going to make 6 copies of this across those, in this case, 6 storage nodes. I'm going to distribute them, you can see, across the 3 availability zones. And remember, because availability zones are independent, isolated data centers, then they're very unlikely to fail at the same time. So this gives us very good durability across one AWS region. For any new write that comes in, we're going to write 6 of these copies. We're going to have a quorum of 4 of them, right? So we don't have to wait for all of them. This gives us good tail latency. So this means that Aurora can handle the failure of one of these whole AZs, unavailability of a whole AZ. Here it's AZ number 1 with unavailable both storage nodes there, and another storage node in another AZ, and your data is still durable. Obviously, you're not available in this case because your availability zone 1's gone down, but you're still durable. Okay, so we dive a little bit deeper and we talk about what is the data that's actually stored in those little pink boxes, right? What's being written down into the Aurora volume? So first, we've divided this volume into 10 gigabyte chunks. We call them protection groups or PGs. And features like repair and heat management are based on those individual units, right? So we talk about parallelism across those units, those PGs. Traditional databases, generally, they write a log of the changes they're going to make, and then they write the actual changes. And they have to do this because in case they were interrupted in the middle, right, they might need to roll back. So they need to write everything twice. This is expensive in terms of cost and in terms of performance. So what Aurora does is it only writes those log records, right? It only writes the change records. It does not write the pages. And so this, and then it knows how to apply them to the page, knows how to turn them into real data so that we can delete the old log records when we don't need them anymore for space reclamation, and also when we need to read those pages back again. It's just writing stuff's easy, it's reading it back's the hard thing, right, if you're a database. So we call this operation, this coalescing operation. So the Aurora storage is smart enough to do this itself in parallel. Your database instance is not doing it. So this is really great for performance. This is where Aurora's performance comes from. But it also underpins a lot of the HA and DR features that we'll talk about soon. So firstly, we'll talk about backup and restore, because your Sky Picture business, we haven't forgotten about it, it's going great, right? Your application developers are deploying, they're doing this often, they're maybe not testing as well as they should be, and then they release accidentally an application patch that's got a bug in it, and it messes up some of the data. Maybe it sets all the shipping addresses for those lovely Sky Pictures to Nevada so that they all come here, right? So that's great for all the folks in Nevada. It's bad for you as a DBA. Your pager goes off. You have to deal with this. But you're not too worried because we talk about this backup and restore thing here, right? So Aurora provides you backup, built-in continuous incremental backup to S3. So each of those PGs is backing up continuously and independently, remember we said they do this independently, to S3. And it's copying those change records, those logs, into S3. And it's keeping them for anywhere from 1 to 35 days, configurable by you in the retention period. And this forms a window from the earliest restorable time, you can see at the bottom there, to the latest restore time. The latest restore time is normally within 5 minutes of the current time for an active database, right? So this means you can roll back to any of those points in time in that window, right? And that what you would do is you would find that point in time, restore from there, probably run some application level consistency checks and decide this is the right time, and then go ahead from there, all right? So what we're going to do is we're going to talk about what happens inside that restore box. How is Aurora able to restore at any point in time? So we've got the same situation here. We've got some a timeline there, if you can imagine my abstract timeline from 1 to 9. And then what we've done is we first have to choose the point at which we want to restore. And so we might use our application logs to find the place where something went bad and decide that it's time number 7 in my case. 8 and 9 have been impacted by that bad deployment. So we choose to restore at time number 7. We decide that is within the LRT and ERT window by looking at the RDS console. You can see a picture at the bottom there. And so what we do is we copy all of the pages, we restore all the pages before that point. Remember the database pages that we've stored, and we also copy out all of the logs up until that point in time, and then we're able to do that coalescing to put the logs back on top of the pages to make new pages up to that point in time. And this is important to get in your head, is that this is happening in parallel in the storage. So each of those PGs is doing it itself independently, really fast. This means it takes seconds rather than hours, perhaps, if you were to do it in a traditional database. This is a real game changer, right? And so each of those PGs is doing it in parallel. Then we're at a crash consistent point now from the database engine's point of view. The storage is consistent. But what might have happened is there were in-progress transactions. And so at this point, the database engine takes over, a little bit different for MySQL and Postgres within Aurora, but the idea is the same, is that we have to discover which one of those transactions were in progress and roll them back. And here we see a couple more were rolled back. At this point, your database engine is ready to go and your database was restored at, in this case, time equals 5. And it's ready for you to go and use. All right, so this is great. You've learned from the mistake of your developers, and we need a better way to do some testing here, right? We're not going to test in production anymore. We want to test on production-like data, though, because that's always important. And so we need a way to do that that's not going to impact the performance on our production database, and it's not going to maybe give us double the cost either. So what we're going to do is we're going to use a feature called volume clone. Volume clone gives us the ability to make a hollow copy, I guess you'd call it, right? A copy-on-write copy of your primary volume at a point in time. When we first create that clone storage volume, it's got no data in it. It's just a set of redirection pointers back up to the primary volume that you can see there, okay? And what we then do is we've made this volume, then we make a database instance to attach to that volume, and we follow some I/O going on here. So when that clone database instance, your test one, wants to read from the database, from the clone database, it'll go down and follow that redirection pointer up and read the original data because it hasn't changed. Now, if the clone needs to overwrite something, maybe because you've anonymized the data for testing purposes or something like that, then we'll break that redirection pointer and then we'll overwrite the clone storage. Only that one piece of clone storage, right? Using the log records method we just talked about before. And so that means we're only having the cost of just that small delta, right? Then we'll read that back again, no redirection pointer involved. Similar thing happens if we need to update the primary storage, because that's still live whilst this is happening. We break the redirection pointer, we copy that original data down into the clone, so now that's frozen in time, and then we can update the original data. Again, just that small piece. If we need to extend either the clone volume or the production volume at any time, that's independent. The volumes don't know about that extra space, so they can just do it independently. No redirection pointers involved. So this can be used for other purposes as well, like not just testing. Maybe you want to run some batch mode intensive operation. We need to freeze it at a point in time and bring up some new database instances to run that. For some weekend processing, perhaps, it's another useful technique that we can use here to increase the resilience of your existing system, of your production system. So I see your hand up. Do you mind if we take questions a little bit later?
Yes, sure.
Thank you. So now, back in Sky Pictures land, so your CTO hears this quote, right, from our CTO, Werner Vogels, that says, everything fails all the time. And this really resonates with you, and I hope it does. This is not a joke, right? It's that everything really does fail at scale all the time. We have to deal with it. So in your Sky Pictures adventure, you're happy with the 3AZ durability story that you've got out the box, no changes required. But we think as the company, we're big enough now that we need to have some better availability story. We're looking for that 4 nines availability that Aurora says we can get. And that equates to about 52 minutes of downtime a year. So what we're going to do is take that next step. To do this, we have to use what we call the MultiAZ pattern. So what we do is we just deploy another database instance. We put it in a second availability zone so that we increase our availability in the face of an AZ disruption. And it's still able to access that shared Aurora storage because there's no storage in there. So there's no replication of data here, right? You can see that orange arrow that says update. That's not replicating data. That's just telling the standby node, hey, these transactions have happened. If you need to look at them because you take over, go and look in the storage. But they've happened, okay? So now we've made what we call an Aurora cluster of 2 nodes. Even if we have a 1-node cluster, we still call it a cluster. You'll see that in the RDS console. Don't be confused. And so now that we've learned about this MultiAZ technology, and your business is still fairly small, right, we've deployed only one of these things. And we've made them the same size. In this case, they're R7G 16XLs, which is the biggest Graviton 3 instance we can make. And so in the event of failover, the idea is that the standby is big enough to take all the load from the primary. This is important, right, because you've got resources there like CPU, network, and very importantly, buffer pool. Okay, so when that first one fails, the standby will be promoted to a primary. You can see it's now just talking to the same Aurora storage. It's able to take over very quickly, and you're able to restore in less than 60 seconds, right? And there's no RPO conversation here. It's the same storage, right? It's only transactions that were in flight which were impacted, which you would expect. So by putting that in a separate availability zone, we've improved our availability. We haven't changed our durability story at all. So now we're growing, this Sky Pictures adventure we're on keeps going, and we need some more horsepower, right? We need some more SQL processing power. And what we want to do is we can offload some of the read-only queries from the writer node, and we can do this by using that standby that we just made. We don't have to do anything in Aurora. That second node is already capable of doing read-only queries. We just didn't ask it to do any yet. So all we have to do is reconfigure our application to go and talk to that secondary node, right? And it's going to do just read-only queries. And that means if any read queries we were doing to the primary, to the read-write node, we can shift them over to the read-only and leave some more horsepower spare on the read-write node as well there. So you can still see that update link is still there. It's still being updated in between, so we have very low lag between the two. And we've got, you can see there's 70% load on the 2 nodes, right? So it's not 100%, we're okay there. But there's a problem if we try and fail over now in that there's 140% load on that remaining 1 node, right? And you can't have 140% load, sorry, I'm not magic, right? So it's greater than 100%. We've got a problem, it's overloaded. So either your performance might be not so good, or even if it's extreme, your availability might be not so good, it might go down. So we need to do something about this. So we just need to make the cluster a bit larger, right? Just like we added one of those replicas, we could just add another one. No extra configuration. You can make this thing a different size if you want to. You just tell your application, hey, you've got some other nodes that you can send your read-only queries to. In this case, we've just put another one. And it's still getting updated in the same way. It's still able to accept read-only queries. We do it in availability zone 3, a third one now, which improves our availability further as well, right? So in the event of the first node becoming unavailable, now both of the remaining nodes are below 100% of load, so we're safe. We don't have an availability or a really bad performance problem. Okay, so now we really like this pattern. and we continue to use it. We say, well, I'm going to make up to 15 of these replicas if I need to scale this performance more. Here's our original one. I had another one the same size like we did before. So no, and another one, maybe a serverless one, which will scale automatically to meet your load, and then maybe some small ones for some background processing or just to manage costs there. And you can change the size of these instances at any time as well. Just deploy another one and terminate the old one when you're ready. This way it'll all take care of itself. So this is fine, but we need to define the order in which we can fail things over. Otherwise, those small instances won't be able to take the load of the big instances. We'll be back to the same problem we had before. So we can set these tier levels. That's a lower numbered tier is the higher priority one for failover. So here we have the two that are tier 0. They will take over from each other in preference over the ones that are of a different tier number. Okay. So this is great, but we've made it a bit complicated now in that we've got a whole bunch of different servers that we need to be talking to. Our application needs to be configured for, and that's hard. And it's a dynamic problem because when failover happens, the writer changes. And when we add nodes into the read pool, then the readers change. So we have this idea of endpoints. We have 2 endpoints by default. We have the writer endpoint, also called a cluster endpoint, and we have a reader endpoint, which represents the set of all of the readers. So these are just 2 DNS names. You can point your application at these 2 names, and Aurora will take care of what's going on behind the scenes. All we have to do is just reconnect, wait for the DNS TTL to come through, and we've got the new nodes. No special. We can see that happens here. So the latency of this failover is the DNS TTL, basically, and a reconnection. So you can also create custom endpoints here. You're not just limited to the 2 we've got here. You might, for example, group a few nodes together and call them the back-end processing endpoint or something like that. It's also a good availability technique to separate your load apart. So this makes the problem, though, a little bit worse because your front-end fleet keeps growing. Maybe in this case, we've got some PHP servers on the front end running our web application. We have some Java things running on the back end, running the back-end service. And so we've got a bunch of connections coming through from the application to the instance. Here we're just going to talk about the writer endpoint, but the same thing happens on the reader side, right? And so a bunch of connections cause a bunch of problems. We've got idle connections using memory, we've got tier-less negotiation, we've got TCP renegotiation, all this stuff that we want to try and avoid. So that leads us to oversubscribe the resources, which ends up having a higher cost or worse performance. So we can use 2 approaches here. We've got connection limits and connection pooling. So what we want to do is we want to reuse the same connection on the back end for different connections coming in on the front end. That's pooling. And we also want to set limits to give performance to the few connections that we can allow, depending on the size of the instance, but we don't want to allow it just to overload completely like we saw in the earlier slides. So packages exist to do this already. If you're using Java, maybe you've got a JDBC driver which gives you some of this already. And that works okay for standalone databases, but not really for clustered databases like Aurora. So we'll dig into that. Our first tool here is AWS Advanced JDBC wrapper. So if you're in a Java environment, this is where you want to be. We have to have special error handling to deal with this fact when a writer fails over, like we saw before inside the endpoint, then the DNS lookup has to happen and all of that. This is all now inside the AWS Advanced JDBC wrapper. And it also gives us this other thing called EFM we can see up there, Enhanced Failure Monitoring. And so this is where the driver is aware of what's going on inside Aurora. It's aware of the cluster topology. And so it's able to notice without using DNS that, for example, a failover has happened and action upon that much faster. And up to 66% faster failover is what's going to happen here. So if you're interested in some more about this, this is an open source project on GitHub from AWS. There's a QR code there which will take you to the GitHub link. I see lots of cameras. I'll just pause for a second. Cool. The other tool we have, so that was the Java side of things. The other tool we have is RDS Proxy. So if you've got a front-end fleet, maybe which is more stateless, like PHP, there's lots of connections. It's not really a good place for us to put a driver like the JDBC driver to deal with that. So we want to insert a managed layer in the middle called RDS Proxy. This is a managed high availability proxy, which will deal with connection pooling and multiplexing that we talked about before. So what's going to happen here is on the reader side, the same thing happens on the writer, but I'll just use the reader for example. I've set a connection limit of 1 from the proxy down to the back end. Obviously, you'd use more than 1 in the real world, but it's too hard to draw on the slide. So here we've got a bunch of queries coming in from the top. The yellow one's executing through proxy at the moment, right? And then the blue one comes through and it executes on the same connection to the back end. So that's connection pooling. And we've got limits too. We talked about the limit of number 1. And so this reuse of a connection will continue to work until we end up in a situation which we call pinning. And that's where RDS Proxy realizes that you've done something in that database session which says that I can't use this connection anymore for another one. I've messed up the state internally. I've made it specific to this session. So that's called pinning. Some of the things you can do to trigger pinning are to use a prepared statement or temporary tables or maybe some locking functions. So we should try and modify your application to avoid this pinning situation. First step is to understand if you're hitting this pinning situation. So there's a CloudWatch metric up the top there that you can watch for that if that situation is happening. So what this does is it doesn't hurt anything. We've just used up a connection that we can't use for something else anymore. It's only going to be used for blue guys now. So when a failover happens, RDS Proxy would normally make that transparent. It's transparent to the yellow and the purple connections here. They didn't notice anything's happened at all. But the blue guy did notice because he was pinned, so we had to recycle his connection and reset it because it was pinned. Okay. So, Sky Pictures business is fantastic. We're doing really well. I'm glad there's some smiles still. And now we've got some investment and we need to grow up. We need to go global. So this brings for you, for the DBA, some new requirements that we need to talk about. And for me to talk about them, it's no good. I'm going to hand over to Grant, and he's going to take you through the next part. Thanks for your time.
Thank you, Tim. Hopefully everyone can hear me. Good? Yes? So as Tim said, the business has grown. We want to have resilience globally now, right? So the easiest way to do that, and the starting way that I always describe, is with backups. So we've got our same Aurora configuration in region A, as Tim had there. And what we can do is we can just take, let's say, hourly backups. We can use the create DB cluster snapshot command. We could have that in a cron job that just happens every hour. And that's going to have a backup available. Then in the destination region, region B, we can do copy DB cluster snapshot, right? And if we do this every hour, then essentially what we get is we get our data durable in multiple regions, right? So you can think of this as asynchronous replication. I know you're thinking like, how is this asynchronous? It's still replication, it's just very big batchy replication, right? It's once an hour, but it's still an asynchronous process, just like any kind of replication. So that works fine, but let's say one of those Sky Picture sales comes in, right? After you've taken that snapshot. Well, that's not going to be in the other region, right? And that's part of the, the timing of this system. So if we do have a failure or a problem in region A, our RPO now, our recovery point objective, is roughly somewhere probably in the 10 to 70 minute range because it probably takes about 10 minutes to copy the snapshot across regions for it to happen. But it's also if you're really unlucky and you took the snapshot and then you fail 59 minutes later, you have that big gap of data, right? So this is why I'm saying it's asynchronous and it's really batchy asynchronous, right? But it is, you do have your data in the other regions. So you can do a restore, right? And that's going to create a volume for you in that new region. And then you can create one or more DB instances, as we said, to paste on your configuration and start up your applications. So you're up and running now. And you'll see that the RTO time, return to operations, is around 60 minutes. Now, this isn't exact, right? Because depending on the size of the thing, how much scripting you have done, it could be smaller, it could be larger. But that gives you an idea. So this is a pretty okay setup. Like, it's better than not having any global resiliency, but you can see I've sort of colored that yellow to say maybe not the perfect solution, but it's okay. Now, one of the things I want to talk about is failure mode. So the classic failure mode of the whole thing goes away. That's really nice and simple. And any of us that know that's not how stuff fails as well, right? Sometimes it fails in interesting ways. And one of the ways it can fail is a network partition. So to you on the outside, it looked like region A is unavailable, but region A is actually still there, still working. It's just not talking to anyone outside, including you. So that sky picture sale that came in, you have automation that's running and saying, I'm going to print that picture off, I'm going to send it out with UPS, off it goes, right? That data, not only did that picture not get replicated over to region B, but that shipping didn't also get replicated, right? So really when we talk about our RPO, it's not just our replication lag, it's also our network partition time. And we'll talk a little bit later in this presentation about how you can deal with that. But it is something I like to bring up because it usually is missed in a lot of these conversations. So this all looks very complex, but we have a nice service called AWS Backup that simplifies all this. So you can set up AWS Backup to do both the hourly or however often backups you want and the copying to another region. So that really simplifies this whole process. But again, the business grows. We want a better RPO than what we've had in this last example. So now we're going to look at global database. And this is based on the technology that Tim talked about that allows us to do storage-only replication. So if you have an existing cluster, you can add it by doing a create global cluster and you add that one to it, or you can start by creating a global cluster and create your first cluster in region A. And then you do a create DB cluster in region B, referencing that it's part of that global cluster. And when you do that, you basically get your Aurora volume in the second region. And at this point, we behind the scenes set up this replication server and a replication agent, and we start replicating the data from region A over to region B, right? And this again is asynchronous replication. So it's not synchronous, there is some lag, but it's very low. So your sky picture cell comes in, boom. Within a second, it's probably in the other region, right? So this is a much better RPO. Now we're talking typically sub 1 second. And this is going to depend a little bit on the latency between those two regions, and I'll show you some examples of that in a second. Still have that network partition time thing we have to think about, but we'll get there. The other really thing I like about this storage setup is that you can do backups in both regions once that's set up. And you notice you don't even have any RW or RO nodes in the second region. We can still back up because we're backing up from the storage, right? So this allows you to have resilience of both the running system and backups, right? So from a compliance perspective, you can say, I have backups in both regions to your compliance folks, right? So that's really powerful. So, gonna have a problem in region A, it's gonna happen, right? And then what we can do over in region B is we can do a failover global cluster. And you'll notice that extra flag, -- allow data loss, right? This is to make sure you know that this is something where the data that was replicating between region A and region B that was still in flight is not going to be in region B. Now, hopefully that's a very small amount, but it still exists, right? So you as a DBA or an administrator has to know that's the case. Once you do that, you can then create database instances and fire up your app and you're good to go, right? So the RTO time on this is probably in the order of, let's say, 15 minutes. Could be a little less, could be a little more again, because you have to create those instances, you have to get your app up, but it can be pretty quick, right? So we made some good progress here on our resiliency. Now, I just wanted to show an example of some real region here. I'm using Sysbench, I'm doing 20,000 writes per second, so it's a decent workload, right? My source region is US West 2, and I'm replicating to three different regions with this example. So the first one is AP Southeast 1, so that's Singapore, for everyone who doesn't know the regions and how they map up. There's too many now. And what you'll see is that the latency is in sort of the 170 millisecond range, because we're literally going from the west coast of the US, a long ways, right? But that's pretty constant. This is an hour-long run. You'll see a few blips. We get one up to 250 milliseconds. So not a lot of variance on this workload, right? That shows how good this technology is. Now, if you go to a closer region, like you're just going across the US from Oregon to Virginia in this example, you're down to like 70-some seconds, right? Much better. Or if you go to Ohio on the east, then you're even less, right? So you can see you can get down into the 60 kind of seconds. If you were going between, let's say, US East 1 and 2, you're probably down into the low 10s or 20 milliseconds, right? So you can, depending on how you choose the regions, this will control basically about how much replication lag you're going to have, right? So if you pick the two regions that are the furthest apart in the world, it's obviously going to get closer to a second. So it's definitely something to think about. So we're happy with our RPO, right? We're down to a 1 second replication lag, but maybe not on our RTO. So let's work on that. So the next configuration is a symmetric configuration. And what I mean by that is we're going to go create our DB instances ahead of time, and we're going to match them up to what we have in region A. Now, they don't have to be exactly the same. They have to be enough, again, to get your work done in the case of an emergency, right? So you just want some at least minimal setup there. So now, the main difference here is you'll see that that update stream that Tim was talking about, we're now doing that from that replication agent to the RO nodes. That means that these nodes now are behaving just like the RO nodes, the read-only replicas, in region A, in that they can be read from. So you can have applications now talking to them and doing reads. And you can do that just to make sure you know where your data is, but you can also use it for the same things that Tim talked about having read-only applications. So again, problem in region A, what are we going to do? We're going to do the same failover command, right? But in this case, it's almost immediate. It's about 2 minutes to transition from being a read-only cluster to being the primary cluster, right? So we didn't have to start anything up. We basically just have to promote it. So this is much quicker now, right? Now let's get to that network partition case, right? So let's say that wasn't an actual failure. We thought it was, but it turns out it was a network partition. Ooh, so my thing is possibly still running there. As soon as region B can talk to region A again, what we're going to do is we're going to go and make that cluster read-only. So we're going to stop taking writes. And this is basically minimizing that network partition time, right? So that's part of the safety valve that is, there. Now again, it still exists, and we're going to talk about another way to help narrow that down again in a few slides. So this all looks good, but now you're only running in one region, and region A isn't, basically your resilience anymore, right? So what we're going to do is we're going to first take a backup of the volume in region A. And the reason we do this is, remember that maybe we have one sky picture that didn't get replicated across in that last 100 milliseconds? Well, that would be in that backup. So if you need to go look at that backup and find the missing data, you can, right? Once we've done that, we start up the replication server and agents going the opposite flow, and we do a synchronization process, because again, those two volumes aren't necessarily the same. So we take and move the data from region B to A, anything that's different. And then once that's done, we start replicating again, right? So now you're back to a full resilient architecture. And this happens all automatically. You don't have to go do anything. The only thing really is that snapshot, looking at that to figure out about your data, because obviously your data is your data, and you're the one that knows what to do there. So now that's all fine in an emergency, but how do you test this, right? Because if you want to have global resilience, part of the thing is you've got to test your failure scenarios, right? Whether it's MultiAZ or something like failover in regions. So we have a switchover command. It used to be called managed failover, which was very confusing to customers and I didn't like. And based on that feedback, we've changed and added one called switchover global cluster. And this works similar to failover, but different. In that the first thing it does is it makes read-only in the cluster in region A read-only, right? And then we're draining the replication queue over to region B, and then we verify that those two volumes are up to the same LSN, so they've got all the same data, right? And at that point, it's safe for us to promote region B, because these all match, right? And then we can reverse set up all the replication, and again, all this happens automatically, and now you're back to a standard scenario. So this is really useful to do testing. Like, we know customers who once a month fail over, run for a while, then fail back. It's good if you want to move regions. You built in a region, now you want to move to a different region. This is also a great technique. We have a customer who switches 3 times a day between 3 different regions, follow the sun with this model. So that tells you how effective this can be if you want to be closer to your customers. And I'll talk a little bit about that from a latency perspective. So far we've talked a lot about durability and really write resilience, right? But it's very important to have read resiliency. Now you get read resiliency whenever you can do writes, but you don't always need to do writes. For example, in our Sky Picture application, when you're just on that website and you're looking at those pictures that Tim showed, you just want to know what pictures are available and what the current price is in the inventory, right? That's all reads. You don't need to do any writes. So you can customize parts of your application to just do that piece, and they can then run on all these read-only nodes, right? Including in region B. So this is nice because if anything happens to region A, those read-only nodes can continue to serve that portion of your website. So all of your website's not available until you do your failover, but at least people can browse and look around still, right? So that separation is a really good technique to get you higher resilience, right? Now, the other nice thing about this is you can also get lower latency for your customers by having those read-only nodes in the region that's closer to them, right? So, but that's kind of a difficult technique, right? Going and changing your code to separate out where you have to do writes and reads. So we got a lot of requests from customers to help simplify this, because what customers were doing was if they needed to do a write in their application, they would have to do something, where they create like a VPN tunnel between the applications, right? And they would forward writes across to it. And that's pretty complex to set up and maintain. So instead, what we now have for global database is we have write forwarding. So by doing an enable global write forwarding on your instance, you now make it possible for a read-write application to connect to it. And when you do that, when you do an update, we're going to forward that write over to the primary region and to the read-write node. And from the read-write node's perspective, it just looks like almost another connection coming in, making an update, right? So it's not anything weird. It's just standard protocol. So once that write goes over there, it's of course going to replicate back. And then you can see your update. So this is a really good technique, but it does have some caveats about how you want to think about using this from a resiliency perspective. So part of the challenge about forwarding writes is about seeing your reads and how you're going to do that. So here I'm showing two specific regions because I want to show specific latencies. So I've got US West 2 on the one side, so we're going from the west coast of the US in Oregon over to East 1, which is in Virginia. So read-write in the west coast, destination on the east coast. So the default mode for our session consistency, or our read consistency, is session level. And what this means is that I want to be able to read my writes in my session. So when I do an update, that's going to get forwarded over to the read-write node and has to get acknowledged back to us. And that takes about 195 milliseconds in this example. And I'm running a pretty good benchmark, so there's a bit of load that's going on here. So when I go to do a select, what's going to happen is we're going to actually wait for that write to get replicated back to us in region B. And so this is going to take 76 milliseconds for that replication to happen, right? But we are able to read our previous writes. So from a consistency perspective, this is really good because we don't have to worry about doing something bad with our application, right? But as you can see now, by putting this on our destination in East 1, we are creating some dependency on that write forwarding network path as well as the replication back, right? So if that slows down, those latencies are going to get higher. Now typically they'll be fine, but you have to, again, when stuff fails, you have to be aware of it. Now the interesting thing for folks is that the next select, it doesn't have to wait because you've not done any write. You're up to date from your session's view of the world, right? So that's only going to take a millisecond or less. So you can get around this by changing to a different read visibility model, but I don't necessarily advise this, but I do explain it. So the next one is called eventual read consistency, or consistency mode. So we do that same update, same latency, 195 milliseconds, right? Fine. The next select takes 1 millisecond, because guess what? We don't wait for the write to come back. But that means our previous write is not visible. So if you're doing an update and then you select that same row back, you're going to get an odd answer, right? And so if your application's not prepared for that, then now you've got a wrong answer, and that's bad. But you can code for this model. So if you code for this model, then that actually helps you with resilience. But you do have to be very careful, right? And we have one other resiliency model, or read visibility model, which is called global. And this is really the strongest one, but also has the biggest impact. So we do our same update, 195 milliseconds, great. We do a select. And this takes a little bit longer because we're waiting for replication, but we're not just waiting for our replication of our write, we're waiting for all the writes that have happened since we did our write. So everything that's happened, we want to see what the global consistency, all the writes are. So it takes 205 milliseconds. And remember, I'm running a benchmark during this run, so there's a lot of things to apply over on the read-only nodes. This is why it takes a little longer, right? Now, the great thing is all the writes are visible, right? So again, from an application correctness perspective, this makes it easy to be correct. The next select also has to wait for any changes, right? So it's also going to take 205 milliseconds. So this is a great one if you want correctness, but as you can see, you're putting a lot of dependency on the network and the replication, right? So I wouldn't advise this from a resiliency perspective. Now, we've talked about having single region replication. You can have up to 5 regions, destination regions, so 6 in total. They don't have to be the same. Here I'm showing a region C. It could be storage only. Or you could make it the same, right? And you could make read-only nodes, and you could have them all running in regions that allow you to get lower latency for those read-only operations. That's really good for your customers, right? If you have this kind of setup, we have an interesting option that you can run. Not many people do this, but it is useful to manage that network partition time. So if you have these 3 regions, and you set that parameter global DB RPO, and that's just a normal Postgres parameter. This is only applicable to Aurora Postgres. Now, the minimum time you can set is 20 seconds. You can set it much higher than that if you want. And how this works is, if you go to do a commit, what we're going to do is we want to make sure that at least one of the replicas lag is below the global DB RPO or 20 seconds. So I check the first one, it's 200 milliseconds. I check the other one, it's 100 milliseconds. This means we're free to commit that commit. We can send that across, right? Because we know that the data is going to be in one or more regions. Now, let's say region C has a problem. It's now got a replication lag of 60 seconds. That's still fine. We can still commit, right? Because we have the one destination we need, region B. Now, oh, a network partition happened. Oops, that's bad, right? So the good news is, what we're going to see is that the lag is going to go up to like 21 seconds because we're not being able to talk to region B as well. And at that point, our commit is going to get blocked. And because what we're saying is we want to make sure that at least we have one region, region B now, that has no more than a 20-second gap of data, right? So this is a way that you can build to ensure that you bound how far behind your replica is, right? Now, I will say this. It's very important if you're going to run this option to have at least 3 clusters in your global setup, right? Because you need at least one to be available. If you only had 2 and region C fell behind to 60 seconds, you would stop taking writes on region A, right? So that would kind of make your resilience actually worse. Because what we're talking about here is sort of a fencing model that just has a timer on it, right? So very useful if you're doing high-value transactions. Like if we start selling sky pictures that were worth $1 million, we'd probably want to run managed RPO. Not for everyone, but a useful technique. Another area that I want to talk about, which is sort of related to global database, but is mostly just about accounts. So if we have our whole setup in account A, that's great, right? That's very typical in both regions, right? That's how you normally set it up. But the problem is if there's some problem with account A, guess what? That global resilience isn't necessarily going to be helping you, right? So what you want to do is have a second account. And with that second account, you can take, let's say, backups from your first account, and you can then copy those to your second account. And again, AWS Backup is your friend here, where it makes it much easier to do this, right? And at this point, you're actually resilient now just not only globally, but across accounts. And so this is really, again, a nice technique to use. So let's just walk back through the journey of what we've done here to get resilience for our Sky Pictures app. So we pick Aurora because it's durable across 3 AZs in a region. We can add more instances to have multi-AZ coverage. We can do global database, which is storage, to get a good RPO. We can add instances there to lower our RTO. We can add multiple regions to give us better resiliency. And we can do backups in each of those regions. And we can have really good results with global RPO if that's a requirement for your application. So with that, I want to thank everyone. There's a bunch of related sessions going on this week that might interest you in this space. And again, thanks again. Please fill out your surveys.